All right, so hello everyone. If someone could just let me know if you can hear me, and thank you, Derek. So maybe just before we get started, I had a couple of announcements to make. So the first announcement was regarding the software, or I guess you would say the kind of GUI application that's posted on the course website, which is called JFlap. So since your assignment 1 is already out, and I can see that some of you had already started it, and some of you actually already finished and submitted it, I would strongly and highly recommend that anyone who wants to write and kind of solve problems for DFAs to use JFlap. And if you kind of don't want to be bothered in learning how to use it, we're going to post a quick kind of demo video that's just going to explain how to use it. And so you'll see that it can be used to write a DFA, but I suggest that you use it throughout the course, so not just for DFAs, but also for NFAs, and then we'll also look at PDAs and Turing machines. So when we get there, I think JFlap is going to be even more useful than it might be right now. So that's the first announcement. The second announcement is actually regarding assignment 1. So because I know some of you already started and finished it, I just want to make it clear what sort of each question is asking for. So let me just get the assignment. So I should have probably pasted it also on the slides, but I'll just kind of read out the question numbers. So for question 1, it's determining what language is accepted by each DFA, and so we'll talk about that, of course, in a second. But for question 1, it's really important that you give a kind of a clear and detailed explanation. So just writing sort of what the language is won't be enough to give you full marks. You actually need to write why you think it's that. So that's an important point that I wanted to let you know. For questions 2 and 4, those questions I told the TA, I discussed it with the TA, and they're pretty straightforward. So if you just give the DFA, then I think that should be enough for full marks. But then for question 3, which is a regular expression, please explain how you got your regular expression. And for question 5, which we haven't seen yet, but we'll cover. Yeah, so Nelson, I'm going to give you an example of an explanation when we look at an example in a couple of seconds. But for question 5, for the minimization, we're actually going to see an algorithm during the tutorial. And so if you just follow the same steps as the tutorial, then that would also be a way of getting full marks for that question. So same steps as a tutorial, which is probably going to be next Monday, or I'm hoping we don't do it Wednesday because your assignment is due Wednesday. So I'm hoping that I can cover the steps for minimization next Monday. So then you'll have almost everything you need for completing the assignment. So for Jonathan, I'm going to give you an example of what I would expect for question 1 when we look at some examples at the end of these slides. So this is still the slides for tutorial 2, and I'm going to go through an example at the end where it asks for what language L is accepted by the following DFA. And if you kind of go through the same process and sort of write the same thing that, or more or less the same steps that I went through, then that should be, oh, there are no classes Monday, you're right. So then it will be Wednesday. Okay, so with that being said, we have a lot of material to cover, so I'm going to go rather quickly for the intro to DFAs and then slow down for the examples, okay? What is a DFA? So a DFA, or a deterministic finite automaton, is a 5-tuple M, where the elements of that tuple are Q, which is a set of, it's a finite set of states, sigma, which is the alphabet over which the DFA is defined, delta is the transition function. The transition function just basically tells you that if you're in a state Q and you read a symbol, let's say A, then what next state do you go to? Okay. Q0 is the unique initial state. So that's when you write your DFA, that's the very first state that you start with. This is the initial state. And F, the set of final states. So final states for DFAs are denoted as double circles. So what you really need to know about DFAs on a very high level, and actually about any finite automaton on a high level, is that you can think of it as just this box. So let's say this box is a DFA. This box has an initial state. It has 0 or more final states, and there are paths that connect the initial state to different states. Okay. And what a DFA does is that it takes a string. So it takes a string W as input, and as output, it either tells you yes or no. Okay. So yes, meaning that W is accepted by the DFA. So in other words, W has reached a final state, and where no means that W is rejected by the DFA. Okay. Yes, a DFA can have no final states. So that's sort of in a high level view what a DFA is. Okay, so the next thing we want to talk about is, we've talked about languages during the last 2 tutorials. Now, what's the relationship with DFAs? So if you have a DFA, let's call it M, okay, then we say that all of the strings, so all of the strings that are accepted by M is equal to L of M. So in other words, L of M is the language. So is the language or the set of strings accepted by M. And of course, there is only one set of strings that is accepted by M. So that language accepted by M is unique, right? So L of M is unique. And if we want to think of it in a sort of more rigorous manner, more mathematical manner, we have this kind of very, very hard to read, very difficult to understand notation. But if we look at it a bit more carefully, it isn't that complicated. Really what it's saying is that another way of defining the language accepted by M, L of M, is to take all of the strings. So this is all of the strings W in sigma star. So all of the strings in your in the set of all strings defined over the alphabet sigma. where or such that if you start at an initial state Q0, then there exists a path that where you're going to start at Q0, follow W, and end in a final state Qm. Okay. So and this kind of idea is replicated using the extended transition function delta star. And all you really need to know about delta star is that it's kind of like delta, except that now instead of just taking a symbol, delta star takes a string. Delta star takes a string W. And so what this is telling you is where do I end up when I read W? So I read W as a string and I start at Q. So of course, where do I end up means what state do I go to? Let's say state P. What state do I go to starting from Q and reading the string W? Okay, so again, this might seem abstract. That's why we're going to go through some examples to make it more concrete. So for now, we're giving you what the language accepted by M is. So here we're saying that the language accepted by the DFA M, which is represented here. So this is my DFA M. This language we claim is the set of all strings over the alphabet 0, 1 that start with a 1. Okay, so now we're going to try to see why we're claiming this. So what are some examples of strings where the DFA accepts that string and where the DFA rejects that string? Okay, so now suppose we have this example 101. So I'm claiming that the language accepted by M is all of the strings that start with a 1. So in theory, I should be able to accept this string W. So how does that work? Well, when you're looking at a DFA and you're following the computation of the DFA, you always start at the initial state Q0, and you can think of your pointer pointing at the beginning of the string. So as I'm going to go through this computation, I'm going to point to the symbols of the string, and those are going to correspond to the location I am in my DFA. Okay, so at the very, very beginning of my string processing, of my string computation, I'm at the beginning of the DFA, I'm at the initial state, right? So that's why we have this symbol here that represents that we start here. So now what happens? What happens is I'm in Q0, right? And I'm reading a 1 next. So what happens if I'm in Q0 and I'm reading a 1? So in other words, what is delta Q01? Well, you just have to look at your transitions here. Here, I'm in Q0, right? And I'm going to read a 1. So that means that I'm going to take this path and go to Q2. So delta Q01 is going to be Q2. And so that's why in the next slide, when I read a 1 and I'm in Q0, I'm going to go to Q2. Okay, so now I'm in Q2, right? I'm in Q2, and I'm going to start reading the next symbol of my string. The next symbol of my string is 0. So what happens? I'm in Q2, I read a 0, so I follow this edge here, this directed edge, and this is telling me, okay, if you're in Q2 and you read a 0, just go back to yourself, go back to Q2, okay? And again, I do the same thing. So now I've read 0, so now my pointer is now at 1. So my pointer is now at 1. I'm going to, from Q2, read a 1. So from Q2, I'm reading a 1. So I'm following this directed edge. And I end up back in Q2. Okay? Because in fact, delta Q21 is also Q2. And because at the end of my computation, so when I finish my string, I've ended up in a final state, I will accept the string. So because when you read or process W, you end in a final state Q2. This implies that W is accepted. Okay, so that's an example of a DFA accepting a string. So what about a DFA rejecting a string? So same idea, but now instead of having a string that starts with 1, I have a string that starts with 0. And in theory, this string should be rejected because my claim again is that L of M is the set of all strings that start with 1 and that are over the alphabet 0, 1. So let's see if that's true. So again, whenever you start the computation of a string in a DFA, you start at your initial state. So it's as if I'm pointing here. So you can kind of think of Q0 as pointing here. Okay. So then what happens? Then I enter the computation. And so what I see is what's next on my string. And so the next symbol on my string is 0. So now I just need to use, again, the transition function. In this case, it's delta Q0. But now instead of reading a 1 at Q0, I'm going to read a 0 at Q0. And so here I can see, according to the graph and according to this directed edge, if I'm in Q0 and I read a 0, I'm actually going to go to Q1. Okay, so now I've read this 0. I'm in Q1, and now the next symbol to read is 1. Okay, so I'm in Q1, and I read a 1. So what happens? According to this directed edge, I just go back to Q1. So that's what happens. And again, I'm back in Q1. Now I'm going to read a 0. So I'm going to read a 0, and I'm again going to go back to Q1. So this is me going back to Q1. And at that point, it's as if my the kind of pointer that's going through my string has ended, right? So it's gotten to the end of the string. So my pointer is at the end of W, but I'm in a non-final state, right? I'm in a non-final state because this guy does not have a double circle, so it's not a final state. So I'm in a non-final state. And so what does this imply? Because we're talking about a DFA, this implies that W or 010 is rejected. And so in fact, what you can see is that if your string starts with a 1, it doesn't matter what it has after this. If it starts with a 1, you're going to start at Q0, you're going to read that 1, and you're always going to stay in Q2, right? So for the rest of the string, how long the string is, you're going to stay in a final state. Whereas if your string starts with a 0, then it doesn't matter what's after your 0. You're going to stay in a non-final state, which means that you're going to always reject strings that start with 0, and you're always going to accept strings that start with 1. Okay, and another term that we sometimes use for this type of state is that they're kind of like a garbage or dumpster states, because once you enter this state, you can never get out of it. Okay. So that was okay. Good. That was the example of running through a machine, a DFA M, and determining whether or not a string would be accepted by that DFA. Okay, so so there seemed to be some confusion initially about a DFA not having a final state. So I'm not going to give you the answer, but if I have this DFA here, and I feel like this has probably been covered in lecture, but if I have this DFA here, then what is the language accepted by M? Okay, and so clearly this is a valid DFA, right? Remember, maybe I haven't defined this. I haven't defined this rigorously, but for a machine M to be a valid DFA, we need that for every state Q. So imagine you have a machine M and you have an alphabet sigma. Then for a machine to be a valid DFA, for every state Q, the cardinality, let's say, of delta when you read a Q, when you're at Q, and you read an input symbol sigma, should be 1. So in other words, for every symbol that you read, there should be exactly one state. So you need this condition to be true, right? And you also need that for every state that you have to have exactly cardinality of sigma edges or cardinality of sigma transitions, okay? So if your sigma is AB, then every state Q should have exactly 2 transitions, A and B, right? So it can't be A and A, that would be an NFA. It can't be just A, that would also be an NFA. It has to be exactly one A and exactly one B, okay? So that's what you would call a valid DFA. And yes, very good. Someone answered. L of M here would actually be the empty set. Okay, so what time is it? All right. So that's for valid DFAs. Now, so someone was asking me what would be an example of a correct way of solving that assignment question, the first assignment question. So I'm going to do, even though it says exercise, I'm going to do this first one and then leave the second one as an exercise. So there are a few ways that I would accept how you could determine what the language accepted by a DFA is. One way, which only works for very simple DFAs, such as this one, is you start listing some of the smallest strings over the alphabet sigma, and you determine which are accepted and which are not. And based on that, you start to see a pattern. And in my opinion, that pattern is usually enough to say, okay, well, the language accepted by this DFA is, and then some general language. So that's what I'm going to do here. So I have this DFA M here. And it looks like, for all intents and purposes, that my alphabet is 0, 1. So by the way, if, for example, you're in doubt in a question, if you only see, let's say here I only see 2 symbols, you can assume that unless it's specified otherwise, you can assume that your alphabet is just those 2 symbols. So in this case, 0 and 1. Okay. So in this case, my alphabet is 0, 1. Now I'm going to list some of the strings some of the smallest strings from 0, 1, and see if I can find the pattern. So I can start with lambda 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, and that's probably going to be enough. So first of all, let's start with the smallest ones. So if you start at Q0 and you read a lambda, so by the way, what happens if you're in a DFA and you read lambda? Well, that's not exactly well defined for a DFA, but in this case, you can just think of it as if you read a lambda, you just stay at Q0. So it's as if you're not moving. And the reason for that is because lambda is an empty string. And so your cursor, right, the pointer that we were looking at just before, isn't going to move because it's always going to stay at the empty string. So that means that lambda, if you read the lambda, you're just going to stay at Q0. So this is obviously not going to be accepted. Then if you read a 0 or a 1, so if you're at Q0 and you read a 0, you get to Q1. So that's not enough to get to Q2, which is your final state. So that's definitely not enough. And if you read a 1, and in fact, if you read any number of 1s, then again, that's not enough to get to Q2. You actually stay at Q0. So that's not accepted. The next string, which is 0, 0, does in fact allow you to get to Q2. Why is that? Because if you start at Q0, you read a 0, you get to Q1. So now you're reading the second 0. You're reading the second 0 and yet you're at Q1. So then you can use this directed edge. You use this directed edge and you get to Q2. And what you can notice actually is if your string starts with 0, 0, and then has any other number of symbols, you're going to stay in Q2, you're going to stay in your final state. And so anything that looks like 0, 0, and then 0, 0, and then anything else is going to be accepted. So is that enough? Is that enough to say, okay, it's just going to be 0, 0, and then any other string? Well, in this case, not exactly. And the reason you can kind of see why that's not the case is because you do have a loop here, which happens if you read a 0. So let's say you read a 0, then you read a 1. So if you read a 0, and then you read a 1, you go back to Q0. But then if you read a 0, 0, then you can actually you can kind of reset your machine and go through from Q0 to Q1 using 0, and from Q1 to Q2 using 0 again, and end up back in a final state. So what does that mean? That means that what we're really looking for is we're looking for the substring 0, 0. Because as soon as you find 0, 0 in your machine, you get to accept it. Okay, and so if you kind of write in detail what I kind of just explained, that to me is an acceptable answer for saying, okay, this is in fact, if you want to generalize it, the language accepted by M is in fact W in 0, 1 star, such that 0, 0 is a substring of W. Okay, so that would be enough. So there's a question, 0, 0, 0 and 0, 0, 1 is accepted as well. Yes, well, in fact, it is accepted because in both of these strings, 0, 0 is a substring. Okay, so that respects this kind of set of strings. So is there a question that I missed? So for every state, there needs to be exactly, yes. And thank you, Rama, for answering the question. Okay, so I feel like that exercise wasn't too hard. I'm going to, are we doing on time? Okay, I'm also going to do this one just because I want to get to the next tutorial. But I'm going to let you do exercises for the next tutorial so that you can also practice. And this one's actually a bit easier, so you'll see that it's not going to be that bad. So what language is accepted by the following DFA M? So we have M here. Well, in these types, so these are kind of very classic DFAs where if you shouldn't really take too long to be able to see what is accepted. I mean, after doing a couple of examples, I don't expect you to just immediately know what the language here is. But after seeing a couple of patterns, you should hopefully be able to decipher what the language is. Okay, so what's going on here? Well, if we want to take a different approach as what I kind of did here, what I used examples, and I just want to look at kind of the logic of my DFA. So what's the logic of my DFA? To start this kind of process, it's the best kind of, my best advice is always think of yourself starting at Q0 and imagine that you have some arbitrary string W, and depending on what the symbol you have at the beginning, at the front of your pointer, what's the behavior of your DFA, okay? So I'm in Q0. It looks like if I have ones, it has no impact on getting to Q1, right? So I can have a bunch of ones, and I'll stay in Q0. But as soon as I have a zero, I can go to Q1 and I can accept. Okay, nice. So I know that I need a 1. So someone's saying must contain only a single 0. Well, let's see. So let's see what happens when I have another 0. So clearly already I can have a bunch more 1s, and that's not going to change anything, right? So that's nice. You can kind of see that 1s here don't really affect what your language, what the accepted language is. So you can kind of think of the 1s as just being extras, okay? So then what happens? What happens if you have another 0? If you have another 0 and you're in Q1, you actually go back to Q0, right? So at that point, you're no longer accepting, right? So now you're back at Q0. Then what if you read another 0? If you read another 0, you're going to go back to Q1, okay? So you're back to Q1 and you're back to accepting. And so you can see that there's this kind of binary flip here, right? There's this binary flip where if you start at Q0 and you read a first 0, then you flip the switch to say accept, right? If you read another 0, you flip the switch to say reject, and so on, right? So what does that look like? Well, when we talk about binary, that's very kind of close to something like mod 2, right? And so what we're actually looking for in this accepted language is for strings W in 0, 1, where in fact you have, it looks like an odd number of zeros. So the string or the strings accepted by your DFA are going to be the strings over 0, 1 star, where W has an odd number of zeros. Okay, and if again you don't see why, just think of that flipping the switch mod 2 kind of example. So if I start at Q0 and I read a 0, I flip the switch to Q1. So that's allowing me to go to 1 mod 2. If I flip the switch back, then if you remember from 232, 1 plus 1 mod, or just like general programming, 1 plus 1 mod 2 is 0 mod 2. So this state is kind of like 0 mod 2, and this state is kind of like 1 mod 2. And so this is the language accepted by your DFA. An equivalent could be something like W in 0, 1 star, such that the number of zeros in W mod 2 is equal to 1. Okay, so I read a mod 3 somewhere and then I got scared. So must contain odd number of zeros. Yeah, good. Okay, good. So someone said mod, a few people said mod 3. I hope it's clear why that's not entirely true, because you can think of an example that's which is like 1 mod 3, but which isn't 1 mod 2. And so that's why mod 3 won't work. And just in general, if in these types of examples, the number of states is equal to the number of your kind of divisor in your mod. Okay. So
Sorry, can you
yes.
repeat like the mod one? I get it, but I didn't get like the second way of writing it.
Sorry, I had a bit of trouble hearing you. Do you think you could speak a bit louder?
Can you hear me like this?
Yes, yes, perfect. Thank you.
Excellent. Okay, just the second way of writing it, can you just like maybe explain it another time, like the one with the mod?
Yeah, I did, because there's already only like 15 minutes left of the tutorial. So
Okay.
Can we do this at the end of class?
Yes, of
okay,
course.
Awesome. Thank you. So the same thing for the person that asked to re-explain, unless that's you. I'll do that at the end of class, because I've noticed that taking questions could be very productive, but also could run counter to the remainder of the class if we don't finish the material. Okay, so moving on to the third tutorial. So in the third tutorial, we're no longer really looking at what's the language accepted by the DFA, but actually how do you write the DFA that accepts the language, okay? So there's a bunch of kind of theoretical ways that suggest how to write and construct DFAs. To be honest, these are kind of nice tricks to know, but in general, I find that just doing examples is a lot easier than kind of remembering tricks. So I'm not really going to go into detail on these kind of rules. But maybe if we look at this same example, which we, or actually, this might be a good occasion to, it was odd number of zeros. Okay, good. So this might be, I might be able to answer the question about re-explaining while also explaining how to write a DFA that looks like this. Okay, so yeah. So in this case, the question is kind of flipped. And actually, I'm not going to do odd number of zeros because we've just seen that. Let's do even number of ones. Okay, so it's slightly different. All right. So what's the idea here? So we want to create a DFA M such that the language accepted by M is all the strings over 0, 1. So my alphabet is 0, 1. So all of those strings over 0, 1 that have an even number of ones. So for instance, the empty string has no ones, right? So it has an even number of ones. Then I could have 1, 1. So that would probably be my shortest string. No, it's definitely my shortest string. Then I could have maybe 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, something like that, right? So I'd have an even number of ones. And in fact, I could have, let's say, 2 ones and a bunch of zeros, and it wouldn't matter, right? So what's the idea here? The idea, especially when we're looking at something like even or like mod 2 or even like just mod 3. So whenever you have modulos, the idea is that your initial state is always going to act as a 0 mod and then whatever you're looking for. So in this case, I'm looking at even numbers, so I'm going to do mod 2. So my initial state represents 0 mod 2. So well, if we want to be very precise, let's say the number of ones mod 2 is equal to 0. So that's what my initial state, initial state represents, okay? Then I have the state that represents 0, so 0 mod 2. Then I'll have another state, because I'm looking at mod 2, I'll have a second state that represents n1 mod 2 equals to 1, okay? And so I'm writing n1 for n1, I'm defining that as the number of ones in W, okay? So what you need to notice is each of these states kind of represents their own case, okay? So if I'm in this state, this means that I have an even, so this means that I have an even number of ones. And so it means that, so imagine I have an even number of ones, right? So 4, let's say. That means that any number of zeros I have won't affect, so it won't affect the modularity of my number of ones, right? So what that means is I can just loop and stay at the initial state if I read zeros, okay? And the same thing applies for this state. So if the number of ones mod 2 is 1, so I have an odd number of ones, then, so let's say I have 1, 1, 1, then any number of zeros is not going to affect that modularity. So it's not going to change the fact that it's odd. So I can also stay at that state if I'm reading zeros. The next thing is, how do I switch from this state to this state? Well, if I have an even number of ones, and I read, so let's say this string has an even number of ones. If I add or if I append another one, then that's going to give me an odd number of ones, right? So what does that mean? That means that if I'm in this state, which remember represents, this is kind of like even number of ones. What that means is that if I read a 1 from here, then I'm going to no longer be even, I'm going to be odd, okay? So now I'm at odd number of ones, okay? So I have an odd number of ones. What happens if I read a 1? That means that I add an extra 1 to the odd number of ones. So in total, I now have an even number, okay? Because remember, if you have an odd number like 7 plus 1, so this is odd, then this gives you an even number, okay? So that means that if I'm in the odd state and I read a 1, then I can go back to the even state, okay? And that's how you would kind of come to the, well, actually I'm not done yet. That's how you would build the sort of architecture of your DFA. And then at that point, you just need to say, what's my final state? In this case, I'm interested in an even number of ones. And so I can make this guy my final state, okay? And that's why this would be a DFA that accepts the language W in 0, 1 star, such that W has an even number of ones, okay? So maybe that kind of clarified this exercise. What about lambda? Very good question. Excellent question. I like that question. So you have a lambda, right? So we agree that lambda should be in this language, right? Because lambda, so what's the number of ones of lambda? It's
0.
0, thank you, yes. It's 0, and 0, remember, don't forget, 0 is an even number. Okay, so what happens if you're kind of reading your input tape and your input tape has lambda? Well, as I mentioned before, for DFAs, the only thing that can happen if you have a lambda as your input string is you're just going to stay at the same state. So the kind of rule is if W is lambda, right, and M is a DFA, delta, let's say Q0 lambda, is always going to be Q0. So this technically isn't correct. You should only use this notation for NFAs, right? So this is not let's say mathematically correct. Whoopsie daisies. Correct. So don't write this in like an assignment, or don't get tricked by this in a quiz. But what you need to know from this, what I'm trying to sort of explain, is that if you have a lambda as your input string, then you're just going to stay at the initial state. Okay, which means that because your initial state is a final state, then lambda is going to be accepted. Okay. So I hope that answers the question, what about lambda? Which is always a very good question.
How can we write it like
Yes.
in an acceptable mathematical way?
It's a good question. You essentially, you don't really explicitly consider lambda when you're looking at transition functions for DFAs. You just never think of lambda here. The only thing you really need to know is that if you read a lambda as your input string, you always stay in Q0. Okay, that's kind of the rule. Okay, good. All right. So that's for this example. All right, we have another example, which I think might be interesting. So far, what did we do? We looked at the DFA M, where M accepts the language W in 0, 1 star, where W has an odd number of ones, right? And then we said we can also create a similar DFA for when W has an even number of ones. What about if we take the kind of intersection, right? So what about if we take the language over 0, 1 star, where that string contains an odd number of zeros, okay, and an even number of ones. So what's an example of a string in L, just to make things concrete? Well, I would want an odd number of zeros, so let's say 0, 0, 0, and then an even number of ones like 1, 1. All right, so the idea here is actually very, very similar to this, except that now what's going to happen is you're not going to loop, right? You're not going to loop on 0 or on 1 when you're on a state. What's going to happen is if you see a 1, you're going to go to a different state, and if you see a 0, you're going to go to a different state. So what's the very, very, yeah, okay. So if we think of the smallest string, again, that we can read, which is lambda, we know that this has an even number of ones and an even number of zeros. And like I said, when you read lambda as your input string, you always just stay at your initial state, okay? So what does that tell us? That tells us that if we're looking at the case where we have an even number of zeros and an even number of ones, then that's going to be my initial state. Okay, so let's just start from there, and I'll explain this along the way. So imagine I start my string here. So at this point, this state is telling me I have an even number of zeros and an even number of ones. And that's because whatever my string is, I haven't actually read it yet, okay? So I have no symbols yet, so I have an even number of symbols, okay? So now, let's say I have a 0. So if I have a 0, that means that I'm going to have 1 0 and no ones, right? So that means that I'm going to have an odd number of zeros and an even number of ones. okay? And so each of these cases have become states. And so it makes it easy to navigate from one case or one state to the other. So in this state or in this case here, I have an even number of zeros, even number of ones. If I read a zero, so if I read a zero, I'm going to go to this state here, which I myself, so it's not like some kind of magic trick where, oh, this just happens to be odd even, right? This happens to be this case. I define the case myself. So I decide that this state is going to be odd even, okay? So when I say odd even, I mean number of zeros is odd and number of ones is even. All right, so at this point, I have an odd number of zeros and an even number of ones. What happens, let's say, if I read again a zero? So my number of ones doesn't change, but my number of zeros does change to 2. And so what happens is I go back to having an even number of zeros and an even number of ones. All right. Next, what happens, let's say, if I read a 1? So if I read a 1, I'm not going to go down here. I'm going to use this state here, which represents an even number of zeros and an odd number of ones to account for that state. So now if I read a 1, right, my number of zeros is going to stay fixed. It's going to be even. And my number of ones is going to become odd. Okay. And same example as before where I have 0 and 0. If I have 1 and then again another 1, I'm just going to go back, right? Because I would flip the odd of the number of ones to the even of the number of ones, right? So so that's if I read another 1. Okay. So now I have 0, 0, 1, 1, and I'm actually back here, which is good because I have an even number of zeros, an even number of ones, and this is the state for that. Okay, so that's good. It means my process is working, right? So now let's do the case that we haven't seen so far is how do we get to D? To get to D, we need an odd number of zeros and an odd number of ones. So let's say I have, again, I add a 1. So I have an odd number of ones now. And I add another 0. So I have an odd number of zeros. So I'm going to use this kind of dimension to say, okay, I'm going to, my number of ones is going to stay odd, but now I'm also going to flip my number of zeros. So it's going to be odd, odd. And now I feel like you can see what the rest of the DFA is. It's just basically a completion of that. Okay, so this would be for the ones, and this would be for the ones. Oops. So now maybe you don't believe me, and you say, oh well, Ches, you only did consecutive zeros, consecutive ones. So okay, fair point. Let's try 0, 1, 0, 0, 1, 1. Okay, that well, whatever. Okay, so you can see the point that they're kind of intertwined, right? So what happens if I have this string? So just first of all, I have an odd number of ones and an odd number of zeros. So what should happen is I should go in state D, right? So let's see if that happens. So I start at A, I read a 0, so I go here. Then I read a 1, so I go here. Then I read a 0, so I go here. I read another 0, so I go here. I read a 1, so I go here. And I read another 1, so I go here. And indeed, I'm back at D. So it does look like this DFA accounts for this kind of language. And so the last step, which is sort of circling in a final state, is just a matter of determining what the case you're looking for is. So here, I want an odd number of zeros and an even number of ones. So what state is that? Odd zeros, right? Odd zeros. So it would be this one. So it would be C. And so here I would make C my final state. Okay, and that's the same as this picture. Okay, so I realize this example is a bit more complicated, But really, it's just a matter of mapping every possible case to a state. And once you've done that, it becomes a bit easier to understand how the transitions go. Okay, so usually silence is a bad sign, but let's find out. Let's do an exercise. Let me give you 2 minutes to do this one, and we'll look at it together to see if DFA construction has kind of been understood. Okay, so 2 minutes. Nabil, why do your states have 2 Qs? 2 Qs. Oh, you mean this? Like why? Oh, that's just okay. Yeah, yeah. That was just because when we had first designed this, the short answer is basically just imagine this was just like D. So that's a short answer. So basically, don't worry about it. The longer answer is we were just trying to kind of map this idea of like Q2, Q3, Q0, Q1 to this idea. But I think that this might be a bit clearer, like the way I did it here, where I list the cases. But in theory, another good maybe note is that you can call your final state whatever you want. So you can call this cat, and you can call this dog, and it's a valid DFA. Okay, so it doesn't really matter that there's curly brackets, but really you don't need to worry about it. It was just to make things a bit clearer. Okay, no problem. All right, so let's say 30 more seconds, just so I can drink some more water. All right, so let's see how this exercise went. So we want to create a DFA M that accepts the language L, where here it's not sort of your usual language, quote unquote. It's actually a union of languages. So we have this language here, and we have this language here. So typically and usually, as a word of advice, if you're trying to create a DFA where there's a union, it's typically a lot easier to start doing an NFA where you write the machine for, let's say, this language L1, then you write the machine for this language L2, okay? And then you kind of just combine them, right? So with lambda transitions, we haven't covered that yet, but this would be the kind of easiest way of doing this question, okay? But because we want to practice DFAs, we're not going to do it that way. So we're gonna forget I just said that, and we're going to go at it strictly DFA, right? So strictly deterministic. Okay, so how do we do that? Well, the first thing that you kind of need to notice when you're trying to create a DFA for a union of languages is you want to check, is L1 intersect L2 empty? So in other words, are these two languages mutually disjoint? Because if they are, then it becomes a lot easier to write the DFA. If they aren't, so if the answer is no, then what you need to do is you need to kind of integrate. You need to integrate the pattern of one language in the other. So that's kind of hand wavy. What does that mean? Typically, to be honest, this doesn't really happen that often because these DFAs are usually quite difficult to write. So typically what happens is it might just be the union of a couple of strings, okay? And then if it's a union of a couple of strings, you just kind of need to hard code hard code these strings so that they're accepted in your DFA, okay? But luckily in this case, the answer is that the intersection is empty because all of the strings in here start with 2 A's and all of the strings in here start with 2 B's because n has to be greater or equal to 2. So this has to be at least BB and then something, right? So the answer to this question is yes. Okay, so that kind of makes my life a bit easier because I can kind of construct the DFA for this guy, construct the DFA for this guy, and kind of join them together. So that's what I'm going to do. So for L1, I want to create a DFA that accepts the language AA, W, so W is any string, BB. Okay, so let's start at my initial state. So my initial state is always where you're going to start your DFA. And also, very important, never forget to put this arrow here, okay? Because if you don't put an arrow there, then I don't know where your initial state is. And if I don't know where your initial state is, it isn't a complete DFA, and so you don't get full marks on the assignment. Okay, so that's just a word of advice. Whatever you do, don't forget to add the sort of incoming arrow for Q0, because Professor Shiri really wants us to be strict on that and really wants us to make sure that the DFAs are correctly written. Okay, so we start at Q0. Okay, so what can happen, right? What's nice about DFAs is that they're deterministic. So it's always a deterministic choice of what can happen, right? In this case, my alphabet is AB. And so I know that from Q0, I can either read an A or a B. If I read a B, that's going to go somewhere in this language. Okay, so I'm not going to worry about the B for now. So let's just say I have some empty machine here. But if I have an A, right? If I have an A, and let's say what's the shortest string I can accept? I would accept that would also be an L1. So that would definitely be AABB. So let's take AABB as an example. So I definitely need to read. So I can't get away from this. I need to read in my machine 2 consecutive A's, and then at the end, 2 consecutive B's. So that means that if I start at Q0 and I read an A, then I go to Q1. Then if I read another A, I can go to Q2. If I read another A, I can go to Q3. And then if I read another, a B, if I read another B, I can go to Q4. And then, so this DFA isn't done, right? This DFA isn't done. But at that point, I would then accept that string. So if I just had AABB, AABB, then I would land in a final state, okay? Again, this isn't a DFA, right? Because for instance, here, I'm missing the V transition. So now what my usual trick is just to fill in the transitions. So fill in the gaps, okay? So if I'm in Q1 and instead of reading an A, I read a B, what happens? Well, in fact, if I have AB, then that's just garbage, right? Because that doesn't look like anything in L1, okay? And because I know that L1 intersect L2 is empty, I don't need to worry about the fact that, oh, that string could be in here, because I know that it isn't. And so if I'm in Q1 and I read a B, then I can immediately go to my garbage. So this is going to be my kind of garbage collector, okay? Because AB and then any string, that would definitely not be accepted, right? Okay, so that covers Q1, right? I have two transitions. Now for Q2. So if I'm in Q2, that means that I must have read two A's, right? So if I'm in Q2, what does that mean? It means that I've read so far two A's. What happens if I read another A? Well, I'm not going to go forward, but I'm not going to reject this either, right? Because my string that I can accept is AA anything BB, right? And so if I have AA and then another A, then this is possibly part of something, right? So basically, I'm going to read anything until I see two B's, and then I'm going to say, oh, maybe I'm done. Maybe I'm at my final state. So that's what I'm going to do. If I'm in Q2, right? If I'm in Q2, remember that means that I've at least read two A's, then I'm just going to keep reading my A's, okay? So that means that, what does that mean? That means that if I have AA and then a bunch of A's, I'm just going to loop here, right? So that's fine that I'm not accepting this string, right? This string wouldn't be accepted, but it has the possibility of being accepted, right? How? The way for that to happen is if you would read two B's, right? So if I stopped reading A's and I got two B's, then I would accept, okay? So, so that completes this state, right? This state has two transitions. Now, if I go to Q3, so if I go to Q3, what does that mean? That means that I read two A's, a bunch more A's, maybe, right? Maybe it's just two A's only, then a B, right? So I've read a B. Now what happens if I read another A? Well, if I read another A, what I can do is, because I won't accept this, what I could do is I could say, okay, this just means that I'm going to expand my W, okay? Because remember, W here, right? W here is any string because it says, right? So I'm going to answer that question at the same time. This says L is the language. So for this particular sublanguage, it's any string that starts with two A's that has a string W in AB, and that string can be any string over AB, right? Because it's AB star, right? And remember, AB star is all of the possible strings over the alphabet. Remember, that's why I insisted to say what sigma star was. Sigma star is the set of all strings over sigma. Okay, don't forget about sigma star, right? So W can be any string over AB, and then I just need to finish with BB, okay? So, so that means that if I go back to this question, and I've read two A's, I've read a bunch of A's, right? So I'm still here. I'm still here. Then I read my first B, so I read my first B, but then I read an A. Then I can basically just reset the search for two B's, because what could happen is I could have another two B's here. So then what I want to say is this A is actually part of this W. And so if that's the case, then if I'm in Q3 and I see an A, I just want to start the search over again for two consecutive B's, okay? And that completes the transition for this guy. Okay, nice. So now I'm left with this guy here, all right? So I'm at Q4, and that means what? That means that I read AA, a bunch of stuff, and then BB. What happens if I read a B? Well, nothing, right? Because then you could say this is your BB, this is your string W, and so you still accept that. So if you see a B, you can just stay at the same place, right? But if you see an A, you just do the same reset as I did here. You reset back to this guy, which is basically always looking for 2 B's in a row, okay? And that's how you would complete the DFA for this language, all right? What time? Okay. So, right, okay. So, because the next 2 exercises are faster, so it's not that bad then. We're kind of going over the time. So that was for this part of the language, right? Now I want to solve the question for this part of the language. So now I'm just going to look at L2, which is at least 2 B's followed by at most 2 A's, right? So if I'm in Q0 and I read a B, then I go to this next state, let's say Q5. So I don't accept yet because I haven't seen 2 B's yet. But now if I read another B, then that's great. That means that I can already start accepting because I have at least 2 B's. If instead at Q5 I read an A, then that means that I have something like BA, and that doesn't look at all like what I want here, and so I can immediately just bring that to garbage, okay? Right, good. So now I'm at Q6. What happens if, so what does that mean? That means that I read 2 B's, right? So if I'm at Q6, what can happen? I can read a bunch more B's, and if I read a bunch more B's, that's fine, because this tells me that I want at least 2 B's, okay? If instead I read an A, then it'll be the first A, right? And here, this condition is saying that I want at most 2 A's, right? And so it's fine if I have an A, right? So this would still be accepted, okay? Right? If, however, then if I'm at this state here, right, and I have a B, then that clearly doesn't look like something like here. So then if I have a B, then I'm also going to put that in the garbage, all right? But what if instead of having a B, I have another A? Then this would be good, right? Because that's greater or equal to 2 number of B's and at most 2 A's. So if I read an A, that's another accepted state. That's another final state. You would accept this string. But then whatever you read here, right? So whatever you read here, if it's an A, that means that you have too many A's. And if it's a B, that just means that you don't look like anything in here. And so in either case, you would also garbage collect there, okay? And so that's why if we look at this clearer picture, this guy is the DFA that accepts L, okay? So hopefully that explanation was worth it, and that that was kind of understandable. Okay.
Excuse me?
Yes.
I just have a quick question.
Yeah. Talk to me.
Can you just please re-explain the W? You told us that it could be a substring
Yeah.
because we're using AB star.
Yeah.
So it could be any substring within AB star?
It can be any string. It can be any string in AB star. So if you try to read this, right, how does this read like? It just says this set contains strings that start with 2 A's, finish with 2 B's, and where in the middle there's a string W, where W can be any string. Okay, that's how you would read that.
Okay, thank you.
Good? Okay, no problem. All right, so that's for this exercise. Now, I'm gonna keep going until maybe here. Okay, so I'm maybe not going to do this one, even though this one would be pretty useful. I might just record myself doing this one, so then you guys can have a bit of a break. Okay, but these two are pretty fundamental, so I'll go over them. All right, so so now we've looked at DFAs. So in theory, you're more or less right. In theory, of course, you need to practice, but in theory, you're more or less comfortable with what are the languages accepted by DFAs and how do you create DFAs that accept languages. Now we're going to talk about a kind of a more abstract concept, which is of regular languages, okay, which was introduced in the last lecture. So what is a regular language? The very simple and very straight definition of a regular language, L, is of a language such that, so L is regular if there exists a DFA M such that the language accepted by M is equal to L. So in other words, if you have some language L, let's say A to the N for N greater or equal to 20, if you want to prove that L is regular, then one way of doing this, so one way of doing this, you're going to see that there's a few. One way of proving that L is regular is create a DFA M such that the language accepted by M is equal to L. Okay, so if in a question, or if in a question it says, is this language regular, or prove that this language is regular, one thing you could do is construct a DFA that accepts that language. All right. So now that's very abstract. Let's look at an example. So we have an example here of a language L, where L is the set of all strings over 0, 1, such that 0, 1 is a substring of that string. So it's all of the strings that have 0, 1 as a substring. And we want to show that L complement is regular. Okay, so how do we do that? So one way, so there's two ways of doing this. One way is, in this case, we have L, so we could write the definition for L complement, which would be W in 0, 1 star, such that 0, 1 is not a substring of W. So that would be, so you would write this language L complement and then find, or I guess construct, maybe construct is better. You would construct a DFA M such that L of M is equal to L complement. So this is one way. This is a very, very good, very correct way of doing it. But the way I'm going to show you is going to enable me to show you a theorem that I think is pretty useful and that you probably actually already saw in lecture. But I always like to remind students or just people in general that it exists. So the second way of doing this, second way of showing that L complement is regular is find, or let's say construct again, construct a DFA M such that the language accepted by M is L. So in other words, find the machine that accepts L, find the DFA that accepts L, then apply a conversion. So convert M to M prime such that non-final states become final states and final states become non-final states, okay? And there's this theorem here that tells us that the language accepted by M prime will be equal to the language accepted by M complement, but the language accepted by L complement by M, sorry, the the language that's accepted by M is equal to L. And so L of M complement is going to equal L complement. And so by this process, we will also have shown that there is a DFA M prime such that the language accepted by M prime is equal to L complement, which means that it would mean that L complement, oh, let's use a different color. L complement is regular. All right, so that's the technique I'm going to use. So let's do that here. So I want to create a DFA M that accepts all of the strings that contain 0, 1, right? 0, 1 as a substring. So if you haven't noticed yet, but I think this was covered pretty like in detail in the lecture, is one sort of easy way of getting started for a substring DFA is just write the substring you're looking for. So in this case, 0, 1. Make the last state the final state. Make the final state kind of a looping state, and then just work around all of the other states so that each of them have, in this case, 2 transitions. Okay, so if I'm in the initial state and I read a 1, that doesn't help me in finding 0, 1, so I stay at the same place. But if I read a 0, so let's say I have 1, 1, 1, 1, 1, 0, then I'm here. And actually, if I read another 0, it's not productive to go back, right? It's not productive to go back. Actually, if I read a 0, I can just say I'm going to wait here and wait to find a 1. And as soon as I find a 1, I can go to my final state and accept. Okay. So this would be the machine M, where L of M is equal to L. Okay. So then I could create a machine M prime, which would just be converting non-final states to final states and keeping all of the transitions the same, and final states to non-final states. So this would be M prime, and then I would have shown, because we have this theorem, I would have shown that L M prime is equal to L complement. And so this implies that because I have a DFA that accepts this guy, right, that accepts this language, then this guy, L complement, is regular. All right. Okay, good. So that's how you would have that. That would be one of the ways to complete this kind of question. Okay, and so yeah, last but not least, let's do this one because I think it's pretty quick. And then this one I'll record and then post it for you to have. Yeah, let me give you 1 minute because for those of you who are here, you're probably motivated enough to do it. So I'll give you one minute maybe to think about it, and then we'll look at the solution. All right, so if you might have noticed, this question was a bit of a trick question because basically, if we look at the language, what's the language? It's basically B, right? Then a bunch of strings U, V, W, X, Y, Z, where each of those strings are in A, B star. And then at the end of the string, we want an A. Okay. So why do I say that this is a trick question? Because really, it doesn't matter if there's 1,000 strings here. It doesn't matter if I have 1,000 strings in between my B and an A. Yes, very good. A very good point. It doesn't matter that, you know, I have 1,000 strings between B and A, because each of those strings are in A, B star. That means each of those strings can be anything. So then if I just take all of this string as just one, so if I just say, let's say S is U, V, W, X, Y, Z, then this is also going to be an AB star, right? And so my language actually simplifies to just B, S, A, such that S is in AB star. And then hopefully it's pretty clear what the DFA for this is. You would start with your initial state. If you read a B, you can go to the next state. But if you read an A, you immediately throw that out. Then if you've read a B and you've read an A, then you could accept. But if you read a B and you keep reading Bs, then it counts as this string here. So you would stay at the same string, right? So that completes. So here I have two transitions. Here I have two transitions. Here, the only thing that's left is if I have an A or if I have an B. If I have an A, I can actually just stay here because anyways, I'm still going to end with an A. If I have a B, I can actually go back and just keep searching for that next A, okay? And then this becomes the DFA that accepts this language. All right, so thank you for your patience. I will, as I said, record this one because I think it might be relevant for your assignment. And I'll post it so that you can have it to kind of go through. But I understand that you want kind of a break before lecture. And so, so that'll be it. Yeah, sure, I can do that. So just for people who want to drop off, that's fine. I'm just going to now answer a bunch of questions. Okay, so Nabil, valid DFAs. So whoopsie daisies. So what is a valid DFA? Okay, if I have a machine M, right, it's a valid DFA if for each state, so if for each state, let's say Q, I have cardinality, right? So imagine this is my alphabet. So I have cardinality or the size of my alphabet number of transitions. So that means that if sigma is, let's say, ABC, then I would have 3 transitions, okay? And so I have cardinality number of transitions, and I have exactly 1 transition for each, let's say, symbol in sigma. So that means that I would have exactly 1 transition at Q for A, exactly 1 transition at Q for B, and exactly 1 transition at Q for C. Okay, so then that means that if there's any kind of disrespect of this rule, so if, for example, I'm at Q and I have just 1 transition, then that's not valid. If I have 3 transitions, but 2 of those are A's, then it doesn't respect this rule, so that's not valid. What else? If I have more than 3 transitions, then that's already not valid. So in kind of more kind of formal terms, you want, because this is called a specified FA, and this is called a over specified FA. So under and over just refers to the number of transitions you have. And so you want it to neither be under or over specified. And maybe one extra note. An extra note is that you can't have a lambda transition. So these are allowed in NFAs, but these are not allowed in DFAs. So you would also have no lambda transitions. All right, and so if for each, so remember this is like a for each, right? So imagine you have an algorithm to check if your DFA is valid. Then what you would do is you do like a for each Q in Q. You would check if delta QA is something, delta QB is something, and for each of these you only have one, so you only have one transition. And you would also check that you have no extra transitions, right? So you don't have like a delta Q lambda, or you don't have like delta QC, okay? So you have to have exactly cardinality sigma transitions, and you have to have exactly one transition for each symbol in the alphabet. Does that make sense? So you can't have multiple transitions. You can't have multiple transitions. Yes, exactly. So yeah, exactly. Very good. So for example, this is not a valid DFA. It's a valid NFA, right? So that's the whole point of NFAs, but it's not a valid DFA. Okay. All right, great, excellent. Any other questions? I'm gonna wait like a minute in case you want to think about it. Yes. Well, you have to realize that this recording is probably like an hour and a half, and so it takes probably an hour to an hour and a half for me to upload it, like to download it. So so right after is as soon as it's possible to upload. Yeah, okay. And I'll also do the same for the extra recording. Yeah. Any other questions?
Hello?
Yes.
I just have a quick question about the assignment.
Yeah.
It's about the DFAs.
Yeah.
So like following the definition you
Yeah.
just provided for like a valid DFA,
Yeah.
like the first example has like a loop, but it's not like it's like kind of like expanded, if that makes sense. But since each state has I guess A/B transitions, it doesn't matter that like A is repeated multiple times, right? Like per state. Like I don't really know how to answer like word this question without you giving me the answer, but
Yeah, there's actually a typo. I'll let the professor. That's so it shouldn't be.
because like Q0, Q1, Q2, like it's kind of like a
Okay,
loop
no, there's
on
no
A.
typo. Okay. Yeah, sorry. Go ahead.
Yeah, so Q0, Q1, Q2, there's like a loop on A, but instead
Right.
of being like a loop on Q0, it's kind of like written out in those three states. But each of those three states have like a transition for A and a transition for B. So following the
Right.
definition that you gave us like I guess.
I'm not going to give you the answer, but
Yeah,
there's 4 states, and you just
Yeah.
said you just talked about 3 states.
there's
So-
4 states. I said there's 3. Okay. Okay. Mm.
You just think about it. Think of
Yeah.
what I just said.
Yeah, because you said, so I understand the number of transitions portion, like for each state, there has to be a transition for each element of the alphabet,
Yeah.
right? But does the number of states matter as well? Because you said mentioned also
No,
something
there
about
can
the-
be
Oh, okay.
as many. There can be 1,000 states, and it could still be valid.
Okay. Would you mind just re-explaining like the cardinality portion? Because that part I don't really
Yeah.
understand.
So yeah, so it's basically, let's say you have like a DFA, like a machine, and let's say we have our alphabet is sigma AB.
Yeah.
Okay.
Mhm.
So the cardinality is just the size of this set.
Yeah.
Right.
Yep.
So that's
Which is
2.
2.
So then what I'm saying is that one of the conditions for the
Mhm.
DFA-M to be valid is
Mhm.
that for every state Q in the set of states,
Yep.
so let me write it out. There must be exactly cardinality of sigma, so 2 transitions.
Okay. Okay. Makes sense.
But that's obviously that's not enough.
Mhm.
That's not enough for it to be valid, because you
Yep.
could have like A, and then that's not valid.
Okay. Okay, I got you. So you
Okay.
need to have you need to satisfy that cardinality portion as well as have like each transition, one
Yes.
transition per element.
Exactly.
Okay. Oh,
So
okay.
it's
I got
yeah.
you. Okay. Okay, cool. Thank you.
No problem. Any other question? That was a good question. No? Okay. Doesn't look like it. So, all right. So, as I said, I'll post the recordings as soon as I can, and I'll also record this extra exercise, which will be useful. Yeah, so as someone said, there's no tutorial Monday, but there will be one Wednesday. Okay. So, so with that being said, have a great long weekend, everyone, and I'll see you Wednesday. All right. Take care.